We ended the last chapter on a genuinely alarming note. A newly oxygenated planet, its atmosphere stripped of much of its insulating methane, was tipping into runaway global cooling. It is worth being direct about what that cooling actually meant. Not a harsh winter. Not a regional ice age of the kind that has come and gone many times since. We are talking about ice sheets reaching, or coming very close to reaching, the equator itself, a planet encased almost entirely from pole to pole. And remarkably, this was not a one-time event in Earth's history. It appears to have happened at least twice, separated by well over 1.5 billion years, under strikingly similar circumstances each time. Scientists call this phenomenon, somewhat dramatically but not inaccurately, Snowball Earth. This is the story of a planet that nearly froze itself solid, twice, and each time found its way back. The first of these two great freezes is the one we already began describing at the close of our last episode. The Huronian glaciation, named for the Huronian supergroup, a thick sequence of ancient sedimentary rock exposed today around Lake Huron in Ontario, Canada, where geologists first identified and studied it in detail. Within these rock layers, geologists have identified distinctive deposits called tillites, jumbled, poorly sorted rock and sediment, scraped up and dumped by moving glacial ice, structurally quite different from sediment deposited by water or wind. Their presence is considered strong physical evidence of extensive glaciation in this specific region, roughly 2.4 to 2.1 billion years ago. Beyond the tillites themselves, geologists have also identified striated pavement surfaces within the Huronian sequence. Flat expanses of underlying bedrock scarred with parallel scratches and grooves, gouged directly into solid rock by embedded stones dragged along the base of a moving glacier. This kind of physical scarring is difficult to explain through any process other than genuine ice sheet movement, adding further physical weight to the glacial interpretation. The Huronian record actually appears to preserve not one, but at least 3 distinct glacial intervals, separated by warmer periods, suggesting this was not necessarily a single continuous freeze, but a turbulent, repeatedly cycling climate crisis unfolding over a span of roughly 300 million years. As we discussed in the previous episode, the leading hypothesis for what triggered this glaciation connects directly to the Great Oxidation event itself. Newly abundant atmospheric oxygen reacting with and destroying much of Earth's previously substantial atmospheric methane, collapsing a major source of greenhouse warming at a moment when the young sun was already providing meaningfully less heat than it does today. In this sense, the Huronian glaciation was not an external catastrophe striking Earth from outside. It was, in a very real sense, a delayed side effect of life's own chemistry. Arguably the first time in this story, though certainly not the last, that biology itself would end up reshaping the entire planet's climate. After the Huronian glaciation finally ended, Earth settled into a strikingly different kind of stability. For well over 1.5 billion years afterward, a stretch of time so long that geologists sometimes only half-jokingly refer to the middle portion of it as the boring billion, the planet's climate. Ocean chemistry and biological complexity all appear to have changed only very gradually, without another global glaciation on a remotely comparable scale. That long calm ended dramatically during the Cryogenian period, a chapter of the Neo-Proterozoic era spanning roughly 720 to 635 million years ago. This period takes its name directly from the Greek for coal birth, and few names in the geologic timescale have ever been more literally appropriate. During the Cryogenian, geologists have identified evidence for at least 2, and possibly more, separate episodes of extreme global glaciation. An older, exceptionally long event called the Sturtian glaciation, and a younger event called the Marinoan glaciation. Precise radiometric dating places the onset of the Sturtian glaciation at approximately 717 million years ago, and remarkably, evidence suggests it may have persisted with the planet locked in an icy state for something in the range of 57 million years, an almost incomprehensibly long single glacial episode by the standards of any other ice age in Earth's entire recorded history. The Marinoan glaciation followed later, ending around 635 million years ago, and while somewhat shorter than the Sturtian event, it too appears to have been a truly global and truly severe climate catastrophe. The genuinely startling scientific claim at the heart of this entire episode is not simply that these were severe ice ages. It is that the glaciers reached, or came remarkably close to reaching, Earth's equator. That claim rests on a clever combination of two independent lines of evidence. The first is, once again, the presence of unmistakable glacial tylite deposits found on nearly every continent in rock dated to this period. The second, more surprising piece of evidence comes from paleomagnetism, the study of magnetic minerals within these same glacial rocks, which recorded the orientation of Earth's magnetic field and therefore the approximate latitude at the exact moment those minerals originally formed. When geobiologist Joseph Kirschvink analyzed this paleomagnetic data from Neo-Proterozoic glacial deposits in the early 1990s, he found something that seemed to defy ordinary explanation. Rock that had unmistakably been deposited by glaciers appeared, based on its magnetic signature, to have formed at tropical, near-equatorial latitudes. On a planet like ours today, that combination is essentially impossible. Glaciers form at high latitudes or high elevations, not at the equator, precisely because equatorial regions receive too much direct concentrated sunlight to sustain year-round ice at sea level. The only way to explain equatorial glacial deposits, Kirschvink argued, was if the entire planet, equator included, had been cold enough to freeze. Meaning Earth's ice caps hadn't simply expanded outward from the poles, but had met somewhere near the middle, potentially encasing the entire globe. And it took years of additional fieldwork on multiple continents before it gained broad acceptance. Confirming a single anomalous data point is one thing. Confirming that the same paleomagnetic pattern at the same time period holds true across separate ancient landmasses that are today scattered across entirely different parts of the globe is considerably more persuasive. And that is precisely the pattern that gradually emerged from subsequent research. It's worth noting, in the spirit of scientific honesty we've maintained throughout this series, that not every researcher accepts this interpretation without reservation. Some have proposed alternative explanations for the observed tillite distribution, including tectonic models suggesting rapid continental drift or unusual rifting processes could place glacial deposits at seemingly low latitudes without requiring the entire planet to freeze. The core paleomagnetic evidence, however, has been reproduced across multiple independent studies and continents. And the general scientific consensus today firmly favors some version of a genuine planet-spanning glaciation during this period. Granting that the planet did experience an extraordinarily severe low-latitude glaciation, a further scientific debate immediately follows. Did the oceans freeze completely solid from surface to equator, or did some liquid water manage to persist somewhere? The more extreme position, often called the hard snowball Earth hypothesis, was formally developed and popularized by geologist Paul Hoffman and his colleagues, who proposed that the oceans genuinely froze over almost entirely, with average global ice thickness potentially reaching hundreds of meters, even at the equator. A somewhat less extreme alternative, sometimes called the SLUSHBALL Earth hypothesis, is supported by certain climate modeling studies suggesting that a completely solid, edge-to-edge global ocean freeze may be difficult to achieve or physically implausible given how ocean currents transport heat. These models instead suggest a thinner band of sea ice, or even a strip of open or seasonally open water, might have persisted near the equator throughout the glaciation. This distinction matters enormously for one of the biggest related questions in this story. How did complex life, including the ancestors of animals that were almost certainly already present in some early form by this point, survive such an extreme and prolonged glaciation at all? A completely solid, sunlight-blocked global ocean would have posed a far more severe survival challenge for photosynthetic life than a version of the planet retaining even limited patches of open or thin, sunlit ice. This remains a genuinely active area of research and, honestly, an unresolved scientific debate. What both camps agree on is that conditions were extreme enough to register as one of the most severe environmental crises in this planet's entire multi-billion-year history. Whichever version proves closer to the truth, life clearly did survive both the Huronian and Cryogenian glaciations. We know this with certainty since we are here to tell the story, along with every other living descendant of the organisms that made it through. One particularly interesting piece of supporting evidence for at least a largely ice-covered ocean during the Cryogenian comes from an unexpected source we've already discussed at length in a previous episode: banded iron formations. Recall that these distinctive rust-red rock formations mostly stopped forming after the Great Oxidation event. Once dissolved, iron had largely been oxidized and stripped out of Earth's ocean chemistry. And yet, curiously, banded iron formations reappear briefly in the geological record, specifically during the Cryogenian glacial episodes, before vanishing again afterward. The leading explanation is genuinely elegant. If thick ice sealed off large portions of the ocean's surface from the atmosphere for millions of years at a time, oxygen exchange between air and water would have been severely restricted. Beneath that ice, deep ocean water could plausibly have reverted to an oxygen-poor, anoxic state, once again allowing dissolved iron, likely still being supplied by ongoing seafloor volcanic activity, to build back up in solution, only to oxidize and precipitate once more when the ice eventually broke up and reintroduced oxygen to the water. Only to oxidize and precipitate once more when the ice eventually broke up and reintroduced oxygen to the water. As for where life itself may have physically persisted, researchers have proposed several plausible refuges. Thin patches of ice allowing some sunlight through, isolated pockets of liquid water maintained by ongoing volcanic or hydrothermal heat, meltwater ponds forming on the ice surface itself during brief warmer intervals, and of course, life continuing much as it always had around deep-sea hydrothermal vents, entirely independent of surface sunlight altogether. Perhaps the most elegant part of this entire story is the mechanism proposed to explain how Earth ever escaped a state that, on the surface, sounds almost permanently self-reinforcing. After all, ice reflects sunlight far more effectively than open ocean water does. So once a planet begins freezing, that growing ice cover should, in principle, make the planet reflect away even more heat, driving further cooling in a vicious cycle. What could possibly break that loop? The answer connects directly back to the carbonate-silicate climate feedback we first introduced back in our episode on Earth's first ocean. Under normal conditions, atmospheric carbon dioxide dissolves in rainwater, weathers exposed silicate rock, and is eventually carried to the ocean, where it becomes locked away in carbonate sediment. A process that acts as a natural long-term thermostat, gradually removing carbon dioxide from the atmosphere. During a global glaciation, however, that thermostat effectively breaks. With virtually all of Earth's exposed continental rock buried under thick ice, rainwater can no longer reach and weather silicate minerals at any meaningful scale. The single largest natural mechanism removing carbon dioxide from the atmosphere simply shuts off almost entirely. Volcanic activity, however, does not stop. Volcanoes continued releasing carbon dioxide into the atmosphere throughout the glaciation, entirely unaffected by the ice on the surface far above them. With its primary removal mechanism disabled, that volcanic carbon dioxide had nowhere left to go, and it is thought to have simply accumulated steadily in the atmosphere for millions upon millions of years. Eventually, models suggest, atmospheric carbon dioxide concentrations may have climbed to levels dramatically higher than anything in Earth's more recent history, plausibly hundreds of times greater than pre-industrial levels, before the resulting greenhouse effect finally became powerful enough to overwhelm the ice's reflective cooling advantage and begin melting the global ice sheets. It is worth appreciating just how slow and how patient this particular escape mechanism really was. This was not some sudden volcanic eruption single-handedly thawing the planet in a dramatic instant. It was an exceedingly gradual process, volcanic emissions continuing at a fairly ordinary background rate for millions of years, with carbon dioxide simply having nowhere else to go, steadily building toward a threshold that, once finally crossed, changed everything remarkably quickly. Once meltdown genuinely began, the same feedback loop that had driven the planet into its icy state now appears to have run explosively in reverse. As ice started retreating and darker ocean water became exposed, that water absorbed far more incoming sunlight than the reflective ice had, warming rapidly and melting still more ice in an accelerating feedback loop. Climate models generally suggest this transition, once triggered, likely happened remarkably fast in geological terms, potentially within just a few thousand years, an eye blink compared to the tens of millions of years the glaciation itself had lasted. With such an enormous accumulated backlog of atmospheric carbon dioxide still present, and now paired with newly exposed continental rock finally available for weathering once again, an intense pulse of chemical weathering is thought to have followed almost immediately, rapidly drawing down that excess carbon dioxide and carrying vast quantities of dissolved calcium and carbonate ions into the ocean. That sudden influx of dissolved minerals appears to have triggered the rapid, widespread precipitation of a very distinctive layer of limestone, deposited directly and consistently on top of the glacial tillites in locations around the world. Geologists call these cap carbonates, in their consistent, close association with the top of cryogenian glacial deposits on multiple continents, is considered some of the strongest supporting evidence for this entire escape mechanism. The resulting climate swing appears to have been genuinely extreme in both directions, from a planet locked in ice for millions of years to what several researchers describe as an intense, short-lived global hothouse, before Earth's climate gradually settled back into something closer to a more familiar equilibrium. Let us take stock of this extraordinary chapter. At least twice in Earth's history, separated by well over 1.5 billion years, this planet appears to have frozen at or near its equator, driven each time by a breakdown in its atmospheric greenhouse balance. And each time it found its way back through the patient, relentless accumulation of volcanic carbon dioxide, unable to be removed by a weathering cycle that ice itself had shut down. The first freeze, the Huronian glaciation, followed directly from the great oxidation event we covered in our previous episode. Life's own chemistry destabilizing the climate it depended on. The second, the cryogenian glaciation, arrived over 1 billion years later. Its precise trigger still less certain, but its extremity and its escape following strikingly similar physical rules. It is genuinely difficult to overstate how significant the timing of that second freeze may prove to be for the rest of this story. The cryogenian glaciations ended around 635 million years ago. Within a relatively short span of geological time afterward, the fossil record begins showing the first clear evidence of complex multicellular animal life. And not long after that, an explosive diversification of animal body types unlike anything the planet had seen before or has seen since. Whether and exactly how these catastrophic freezes and their dramatic aftermaths may have helped trigger that explosion of complexity remains one of the most fascinating open questions in this entire series. And it is exactly where we are headed next.